So for the law of inertia, we have the example of a billiard table without friction, also without holes, but that doesn't matter. So there is no friction here, and a ball will travel in a straight line with the same speed as long as there is no force interacting. Of course, you see that the any one of these balls here are interacting with the sides of the billiard table and with each other. But look, for example, at the blue one. Whoops, not anymore the blue one, maybe. Maybe now the orange one, as it just travels in a straight line until it interacts with something else, like the sides. But otherwise, they just keep on going. That's what inertia means. As I said, I turn off the friction completely, so all 5 of these here are actually never going to stop. And I'm going to turn on the friction in just a moment. Okay, friction is turned on now. And notice that they become really slow. Unfortunately, I was not able to actually produce friction between the table itself and the balls. That's why they keep on rolling. But other than that, every time they hit, there's some friction in between the sides and each of the balls and slowing them down. Okay, again, frictionless, so we have inertia is the only thing that applies, and as long as there's no force acting on them, they will just keep on going. I took one of the sides out, and as you can see, they just keep on going, and they're going to go forever off the screen. So here we have a force applied to a mass, and that would be Newton's second law. Acceleration equals force divided by mass, or force equals mass times acceleration. And as we can see, as this force is being applied to this object here, the car, it gets faster and faster, and that's the acceleration that you're seeing. So this little arrow here means the force, pushing it to the left. On this car here, I have doubled the force. So with more force on the same mass, we obviously get more acceleration. So it's getting faster, much faster. So here we have now a truck to which the same force is applied, but of course the truck has much more mass, so the acceleration is going to be less. In the previous examples, we have seen that a force can make an object move faster, accelerate it. Here, as the car is traveling to the lower left, we will see that a force is also able to change an object's direction. Okay, this is Newton's third law, action-reaction principle. So here we have a linebacker rushing the quarterback. Happens to be a really massive quarterback, tall. And the linebacker apparently is a little bit lightweight. And he carries a football too, but kind of ignore that. So here he goes at a relatively large speed, and as soon as he hits him, well, he's exerting force on the quarterback, but notice there's also force exerted on him. So here we have the quarterback running at the linebacker, who seems to be just standing in the way. And again, the linebacker in this case receives the force, but the quarterback is also being slowed down, is not running as fast as he used to. So overall, we have equal and opposite forces between the two, and even though they exert the same force on each other, the one to whom it makes more of a difference is the one with the lesser mass. As you can see, the one with the lesser mass gets a larger acceleration, which means we're actually taking Newton 3 and going back to Newton 2. This is a reiteration of what an acceleration actually means. And I'm going to start out with Newton's second law, which says that the net force equals mass times acceleration, or just one algebra step, acceleration equals net force divided by mass. Net force means all the forces that act on one object combined. So there's just one vector that we're going to come up with, and now that one vector for the net force actually is parallel to the acceleration, so the net force points in the same direction as the acceleration. The two are combined by simply dividing the net force by the mass. That actually I won't do throughout my explanation here. I don't want to do any calculations, where therefore we're not going to add or subtract anything. Therefore, when we look at the vectors, we're also not going to be able to combine them simply because I'm not dividing by the mass. I just want to keep it conceptually here. Okay, so we have a net force that produces an acceleration by dividing by mass. The acceleration produces a change in velocity. Same thing. I would have to actually multiply that by time in seconds, for example. But I'm not going to do that. I just want to keep it conceptually. That's also why you see down here the units: force in newtons, acceleration meters per second squared, velocity in meters per second. You cannot add vectors directly. You would have to divide by mass, multiply by time. But as I said, we're not going to do that. I just want to point out especially that an acceleration produces a change in velocity, which then means decrease in speed, increase the speed, or change direction, because velocity means speed with direction. So if I change the velocity with an acceleration, I either decrease the speed, increase the speed, or change the direction. So here's the example. We have an airplane sitting on a runway. There are several forces acting on the airplane. Weight is pulling it down. The support force of the runway, well, supporting it upwards. The propeller is on yet, but it doesn't produce any thrust yet, which means the brakes must be on. So the velocity right now is 0. The airplane is just standing there. And since the support force and the weight cancel each other, and we don't have any thrust yet, the net force is 0, therefore the acceleration is 0. Therefore, since there is no acceleration, the velocity is not changing and it stays constant, and if we keep it this way, then it will always be v equals 0 meters per second. That's the law of inertia. Something at rest will stay at rest, but that's a little boring. We want to continue here with that something does happen. So let's say that the airplane is now starting to move to the right. In order to do that, we need a net force, so we put the thrust on. So we have a net force with an acceleration in the horizontal. This is what I said earlier. Net force and acceleration are always parallel to each other, or with each other. We have now actually 4 forces: weight down, support force up, thrust forward, drag backwards, or friction because it's still on the runway, and all those 4 added together comes out to the net force, which then produces an acceleration according to the mass
of the airplane. And now that it's accelerating, the velocity indeed is increasing. So we have some velocity here. Notice that I cannot add these vectors because they have different units. And as I said, I just want to keep it conceptually. Okay, so the oops, I meant to use a different color here. The velocity of the airplane is now increasing, perhaps 1 meter per second, 2 meters per second, and so on. And once it's at around 30 meters per second, it will be fast, which is about 60 miles. That airplane is going to be fast enough for liftoff. Okay, what I need for that then is that the net force and the acceleration need to point at least partially upwards. So what we have here now is that we have weight pulling down, thrust to the right, drag to the left, support force still from the runway up, but now we also got lift, and that all these 5 vectors in this case, 5 force vectors in this case, added up give us a net component that also goes up. So what is happening here now is that the velocity is increasing still, but it's also starting to point upwards. By the way, I'm also not changing the length of the arrows here because I think that would be just a little bit too much. So it's starting to lift off, and so this one here would be a minute not just to the right, but to the upper right. Okay, now the plane is flying, and I'm going to take the runway away. Okay, now the plane is flying and it's gaining in altitude, so it's getting faster, and let's say at some point it has reached a speed of 50 meters per second, and it's still flying to the upper right. And it still is increasing its altitude, gaining altitude. So now the pilot decides that she wants to keep it at a certain maximum altitude. So she needs to change velocity. Right now it's pointing up, but she needs to change it in order to keep it horizontal. Well, that needs a force. So she applies a force that will now point downward, at least partially downward. Now that doesn't mean that the airplane is now moving downwards. What it means is that the velocity will change its direction. So going from up, it will move towards horizontal. By the way, it's also still getting faster, so maybe I'm going to change this one here to 60 meters per second. It's actually a little fast for that little airplane, but that's okay. So the net force is downward until that velocity is then constant horizontally. Notice that in order to do that, she would have to decrease the lift. So the lift would have to be less than the weight, so that the weight actually slows the airplane down on its ascent until it has reached a cruising altitude. Now the pilot decides that I just want to keep going at that 60 meters per second at constant altitude, which means I want to keep my velocity constant, and I can only do that if I have no force. So a moment ago, actually, the airplane just moved to the right and still getting faster. Now it just keeps moving to the right at a constant velocity. There's no force. Acceleration is zero. Velocity is constant. Now the pilot decides, oh, I want to fly a little slower. So what she can do is she can reduce the thrust, so that overall she would have, with more drag than thrust, she would have a net force pointing to the left. So I'm going to turn these arrows around. I'm going to change the writing here. I said don't add the vectors. We can't do that because of the different units. Um, but we can do it only conceptually. Now that means with the net force pointing to the left, so there is more drag, that means also that the acceleration is to the left. Since the velocity is to the right, that means that the velocity is decreasing. So the speed is decreasing, it's getting slower. Let's say that she's flying only at 45 meters per second at this point. Now she decides it's time to land. Actually, oh, I should have taken this one away here first. So it's time to land, but I need to be at approximately the same speed first here. So let's keep it at 45 meters per second. So actually, let's move this back in here. So it stays at 45 meters per second. Still moving to the right. But now I want to land, which means I have to go down. In order to do so, I need a force, and that force needs to point down. And notice that that force now changes the direction of the airplane. It's going down, so the airplane itself is going to the lower right. Now she decides, I don't want to keep on being almost here in free fall. I don't want to fall faster and faster, so I may want to actually keep the lift equal to the weight, which means I have no net force, and my acceleration is 0 therefore, and the velocity is constant, but I'm also already going down, so that still means I'm going down, but my net force is 0, and my velocity is constant. That's exactly what it means. So she keeps going down. Now she's going to see the runway. So the runway is going to come into the picture here. She may want to slow down before she gets there, so she reduces the thrust, and that will reduce her velocity in the horizontal. So perhaps this one here will be 30 meters per second, just as her takeoff speed was earlier. So now she is approaching the runway. And there it is. And now, oops, didn't mean to do that. I think I moved this way. There we go, there we go. Okay, now, once she has reached the runway, of course, the velocity needs to be horizontal again. And that means that the force and the acceleration actually momentarily have to point upward in order to make the velocity going from pointing down towards horizontal. How did that happen? Well, it's the landing on the runway. Now there's the support force from the runway pushing up, and that gives a net force that points upwards. Okay, now of course she is slowing down on the runway, so she needs a net force to point to the left. So she increases the drag on the airplane, and that decreases the velocity then to, at some point, to 0 meters per second. And then she is at a standstill, and then there's no drag left because she wouldn't be moving anymore, and there is no thrust either, and the net force is 0, the acceleration is 0, velocity is constant, and the airplane is just standing there. And with that, I hope I was able to explain what it means when you have an acceleration which is caused by a force, by a net force, what it means to the velocity, how the velocity, the speed is increasing, decreasing, how it changes direction.